I just covered the significant advantage that makes the fixed wing drone the champion of endurance and range. They are incredibly efficient mission purpose built for covering vast distance. However, in the world of engineering, every design choice is a trade-off. To gain those powerful ability, fixed wing drone must sacrifice performance in other key areas. It is crucial to have an honest and clear understanding of these limitations, not to diminish their value, but to ensure we always select the right tool for the right job. This slide will walk through us through the key operational challenges and limitations inherent in fixed wing drone. The single most significant limitation, and one of the most which other terms, is no hovering capacity. As we established, fixed wing drone relies on constant forward motion of generation lift over its wing. If it stops moving forward, it stops flying. This ability to hover in a fixed position immediately makes it unsuitable for huge number of applications. Any task that requires stationary observation is off the table. You can you cannot use a fixed wing drone to perform a detailed close-up inspection of a specific blade of a wind turbine, or to provide persistent aerial security over a single point, or to act as a stable platform for filmmaking, capturing a static shot. The best it can do is circle a point of interest, which is fundamentally different and far less precision capability than the rock steady over a multirotors. This inability to hover leads directly to the next major logistic challenge: runway requirement. Based on the fixed wing drone needs a built-up speed to take off, it typically requires a dedicated runway, a long, flat, and a clear strip for landing for a safe takeoff roll. The same is true for landing. It needs to glide, and it has should have enough space to touch down and slow to stop. While some smaller models can be launched using handheld launchers. We have just examined the limitation of fixed-wing drone, highlighting their inability to hover and their need for large operational area. Now, we turn our attention to drone classification that was specifically designed to overcome those exact challenges. Multi-rotor drone. This is configuration that most people pictures when they hear the word drone, and for a good reason. Their popularity has exploded because they offer incredible versatility and precision control. Their fundamental design principle is simple yet powerful. They use simple multiple propeller working in concert to generate lift and provide a level of maneuverability that is simple and matched by other types of drones of aircraft. Let's introduce different forms of multirotor can take their basic principle that allows them to fly. A multirotor family has several common configurations, which the main difference being the number of propellers they use. The most popular and widely used by far is the quadcopter, which is four-rotor design. It strikes the perfect balance between mechanical simplicity, the cost efficiency, and agile performance. It is the standard of the vast majority of consumer and pro-consumer drones used for photography, videography, and general recreation. Stepping up from that, we have hexacopter, which is a six propeller. It offers immediate and noticeable advantage over quadcopter. The additional 2 points of lift provide a significant increased stability, making it smoother performer in a platform, especially when flying in windy conditions. This increases the power also means it has greater lifting capacity, allowing it to carry heavier payloads like professional camera or sophisticated scientific sensors. At the top end of the common configuration is the quadcopter, which has eight propellers. The design offers absolute maximum wind stability and lifting power. The incredible stable flight characteristics makes the performance We just seen the different configuration of multi-rotor drone from the common quadcopter to the heavy lifting octocopter. Now let's why explore the why behind these immense popularity. What are the specific advantages offered by this design that have led us to dominating both consumer and commercial market? The answer lies in the unique combination of simple physical form and the incredible sophisticated digital control, creating the platform that is flexible, accessible, remarkably precise. These key benefits make them perfectly suited for a vast array of modern drone applications. The most immediate and transformative advantage of the multi-rotor drone is its capacity for vertical takeoff and landing, or VTOL. This is a direct answer to the biggest logical challenge faced by fixed-wing aircraft. Multi-rotor aircraft doesn't need an airway, a catapult, or a recovery net. It can lift off from land on a spot on a spot. No bigger things is required for itself. It unlocks the incredible operational flexibility. You can launch a mission from a small boat in the middle of a lake, a dense clearing, a cluttery constructional site, or a city roof. This ability to operate most anywhere without the need of a specialized infrastructure is a primary reason for this widespread adaptation. This operational flexibility is enhanced by their physical design. The multi-rotor is typically features a very compact design. The components are centralized and the arm that holds the motor are often foldable, allowing many high-performance drone to be stored and transported in a small backpack. The portability is huge advantage for professional in the field. Furthermore, their compact nature allows them to fly in confined spaces where fixed-wing drone could never go there, such as indoor, under the bridge, or through a narrow urban canyon. This is coupled with a relatively low manufacturing cost compared to the complex aerodynamic surface and the structure of a fixed wing. A multi-rotor frame is much simpler to It has praised the multi-rotor drone for its incredible agile, precise, and go anywhere VTOL capacity. These advantages has rightfully made it the most popular drone configuration in the world. However, no design is without its drawback. In engineering, every choice involves a trade-off, and the very design that gives the multi-rotor is the strength also creates a distinct set of limitations to be effectively non-operator and planner. We must have a clear-eyed view of these challenges to understand when a multi-rotor might not be the right tool for job. The most significant limitation and one of the underpin of, of the others is its high energy consumption. The multi-rotor core functionality using a multiple propeller to generate direct brute force lift is also an Achilles heel. From the moment it takes off, it is locked in a constant power hunger battle against gravity. Unlike fixed wing drone that can glide efficiently on its wing, the multi-rotor motor must continuously work at high speed power just to keep it without falling. There is no coasting, no gliding, just a constant expenditure of energy. This constant high demand for power leads directly to the most widely felt drawback, limited flight time. As the slide clearly illustrates, most multi-rotor drones under normal operating conditions have a flight time of only 20 to 30 minutes. When you compare that to 1 hour, 2 hours, or even more of fixed wing drone, the difference is staggering. Its short endurance is the major constraint on its practical application. The direct and inevitable consequences of this limited flight time is severely restricted range. An aircraft can only fly so far. It has to return back to home within the stimulated lifetime of the battery. The battery life dictates the operational radius. This this makes the multi-rotor functionally We have now thoroughly compared the mainstream multi-rotor and the fixed-wing drone, understanding their respective strength and weakness. But there exists another important class of aircraft that clearly bridges the gap between the two, the single-rotor helicopter drone. This design takes the classic time-tested principle of conventional helicopter and scales them down into an unmanned platform. The result is a powerful and efficient machine that combines some of the best features for both multi-rotor and fixed wing, creating an unique and highly capable tool for demanding professional grade application. Let's look at what defines these drones and specific advantage and limitation they bring to the table. The key characteristics of single-rotor drone sets it apart immediately. Like the multi-rotor drone, it possesses a crucial ability to hover and perform vertical takeoff and landing. This VTOL capacity gives it flexibility to operate them from confined area without the need of a runway. A feature essential for many field operations, where it truly begins a diverge from typical multi-rotor in high payload capacity. A single long and aerodynamic efficiency main rotor can generate lift more efficiently than multiple small propellers. This allows the helicopter drone to carry significantly heavier and more sophisticated payload, such as high-end LiDAR scanning system, a large format camera, or even a tank for agricultural spraying. This heavy lifting ability is often powered by fuel engine, while the electric version exists. Many single rotor drone uses a small internal combustion engine. As we know, the high energy density of liquid fuel compared to the battery allows for a massive increase in flight time and pushing endurance for minutes to hours. This unique set of characteristics creates a distinct balance of advantage and limitation. On the plus side, the single rotor drone boasts much higher efficiency than the We have journeyed through the entire landscape of drone technology, looking at and distinct advantage and limitation of each major classification. We saw the incredible endurance of the fixed-wing drone, but noted their need for runway. We celebrated the amazing flexibility of multirotor, but acknowledged their frustratingly short flight times. We This has always been the fundamental trade-off in the drone world. But what if you didn't have to choose? What if you could have it all? The slide introduced the aircraft that aims to deliver the fixed-wing hybrid VTOL drones. This representing the cutting edge of drone technology, an advanced design that seeks to combine the best of the both worlds into a single capable and adaptable platform. Let's break down how this no compromise solution works by looking at the comparison table. First, takeoff and landing. A traditional fixed air fixed wing drone needs a runway, limiting its operational limiting its operational area. A multirotor has complete freedom with its vertical takeoff capacity. The hybrid VTOL takes the best option. It takes off and lands vertically, just like a multirotor, completely eliminating the single biggest logical constraint of the fixed wing operation. You get all the range without needing the specialized infrastructure. Next, let's look at the range and speed. Here, the multirotor is limited and slow, while the fixed wing is long range and fast. Once the hybrid VTOL has taken off vertically and reached a safe altitude, it undergoes an remarkable transformation. It transitions from forward flight, and its wing takes over the job of providing lift. In this mode, it behaves exactly like the fixed wing drone. Inherits its incredible efficiency. It makes the hybrid VTOL offers the same long range and high speed performance that makes the fixed wing drone so valuable for large scale missions. Finally, we have maneuverability. The fixed wing is less agile, while multirotor has high maneuverability. This hybrid VTOL again We have now seen the full spectrum of drone type, from the endurance-focused fixed wing to the incredible adaptable hybrid VTOL. For our final section on different drone classification, we are going dive back into the physics of the common configuration, the multi-rotor. We have talked about what they do and the advantage they offer, but now we'll explore how they do it to manage the fundamental level. Understanding the dynamic of forces, torque, and however is the key appreciation. mm, However, is the key to appreciate the incredible engineering that makes these missions agile enough. It is a beautiful dance between simple mechanical principles and highly complex electronic control. Let's start with the basic principle. At the heart of every multi-rotor drone is an asynchronous motor, more commonly known as brushless motor. These marble are of modern engineering capable of spinning at an incredible speed with high precision and efficiency. These motors drive rigid propellers. As the slide states, the principle is straightforward. Generally, the more rotating propeller you have, and the faster they spin, the greater upward thrust you can generate. This is the brute force that gets the drone off the ground. The diagram on the slide shows this flow of energy perfectly. An electric current is drawn from the battery and fed into the brushless motor. The motor converts the electrical energy into mechanical energy, generating torque that spins the propeller. The propeller, an airfoil like a wing that converts the rotation into aerodynamic thrust by grabbing the air and ejecting the powerful downward air force, airflow. That downward push creates an equal and opposite upward reaction. We call it as lift. By generating the lift is only half the battle. To have a stable, controllable aircraft, you must manage the force of rotation or torque. This critical concept in multi-rotor dynamics. When the motor spins a propeller in one direction, Newton's third law dictates that equal and opposite rotational force is We have now completed our journey through various types of drone and the physics that allows them to fly. For the final section, we are going to step into the shoes of an engineer. The designing and building a successful drone is far just more than assembling those parts. It is a complex and fascinating balance act. The engineer must constantly juggle competing priority and navigating the unforgiving laws of physics that governs how size, weight, im- uh, how size and weight impacts the performance. This slide will give us insight into the key design consideration that every drone engineer faces and the crucial concept of scaling law. Let's begin with the three pillar of drone design. The first and foremost is the power consumption. This is almost always the primary concern because it directly dictates the two most critical performance metrics, flight range and endurance. The amount of time a drone can stay in the air and how far it travels fundamentally limited by its power source. For the vast majority of drones, this means battery technology is the single most important factor. The push for lighter, more energy dense battery is relentless quest in the drone industry because every improvement, no matter how small, has a significant impact on what drone do drone can do. The second key consideration is the flexibility and speed. It isn't just about drone speed in straight line, it's about overall agility. This includes its ability to maneuver effectively in complex cluttery environment like waving through dense forest or inspecting an underside of a bridge. It also encompasses the drone's responsive time, how quickly and precisely it reacts to the control input of the pilot or autopilot. For applications like high-speed drone racing or tasks that requires avoiding high-moving obstacle, this responsiveness is paramount. The third pillar is the survivability and strength. A drone is a tool that operates out in the real world, and it need to be tough enough to handle. This way, designing for environmental durability, ensuring the drone can withstand rain, dust, and various temperature. It also involves the designing of collision resistance. While no one wants to crash, accident can happen, and a well-designed drone can often survive minor impact with minimal damage. This aspect, this aspect of strength is also intricately linked to safety, ensuring the drone is robust and reliable to both itself and everyone around it. Now, let's look at how these considerations affect one by one in one critical factor size. You can't just take a drone design and make it bigger or smaller without fundamentally changing its performance. This is governed by what we call it as scaling law. The most critical factor has mass issue. As you increase the drone size, its volume and therefore its mass increases with the cube of its dimension. However, the surface area of the propeller or the wing only increases with the square of its dimension. This means a larger drone becomes disproportionately heavier, requiring exponentially more power to lift and maneuver. This primary challenge is drone designing. This final performance relationship leads to important trade-offs. For application that requires high agility, the preference is almost for smaller, more compact drone. A smaller drone has less mass and inertia, allowing it to accelerate and change direction much quickly, making it perfect for racing or indoor inspection. Finally, when Every design must balance performance, cost, and complexity. A large dome doesn't isn't just heavier; it is more expensive. It also requires larger motor, more powerful and costlier battery, and stronger one with more robust frame. As the graph uh, uh, yep, as the graph on the slide suggests that there is a trade-off between them, finding the sweet spot, the perfect balance between power, agility, and strength, and all while managing the constraint of size, mass, and cost. It's a true art and science of modern drone designing.